Alright, so in this video, we're going to be talking about pretty much everything derivatives, okay? We're going to be talking about what a derivative is, we're going to be going through the different derivative rules, and we are going to be talking about derivative properties, and of course, doing practice, so I'm not just talking at you, right? We're doing some stuff together. So without further ado, let's hop right into this. So here's kind of the rundown of what we're going to be doing in this video. We're going to start off talking about what a derivative actually is, okay? If you don't know what a derivative is, then none of what we're going to go over here means anything to you. Okay, so the second thing is the derivative notation. Here's why we're going to go over the notation pretty in depth. When I was in calculus, okay, there was all this different notation for derivatives, and I got really caught up with it. I didn't really understand completely what was going on. So I feel like if I go over that notation with you, it's really going to help you understand kind of what the problem or what the example is even telling you. Okay, the next thing that we are going to talk about is power rule. That's our first rule for taking derivatives. We're going to go over derivative properties, okay, before we get into the other rules. We're going to go over derivative properties so you know kind of the different things that you can do either with derivatives or before you take a derivative, things like that. But anyways, we also have some other derivatives that we're going to talk about, stuff that kind of has its own rule that doesn't really follow power rule. Okay, then we're going to talk about product rule, we're going to talk about quotient rule, we're going to talk about chain rule, so the other three rules. And we're going to do a quick review. Of course, we're going to do a review on all of this stuff after we go through it all. And we're going to talk about the definition again. I kind of wrote myself a little note that I forgot to erase. This says go back to definition. But so that's kind of what we're going to be talking about there. And then we're going to do some practice problems all together. We're going to be doing some practice problems for each rule individually before we get into those practice problems at the end. But I feel like those practice problems at the end are going to be a great chance for you to just really, set everything in concrete. You're gonna do really well with derivatives, hopefully after watching this video. All right. So let's get into it. What is a derivative? So a derivative represents the rate of change of a function, okay? And, okay, what's a rate of change? What do we call the rate of change of a function? We call that the slope, right? The change in y over the change in x. That's the slope, okay? So we'll write that down right here, okay? That is the slope. Okay, we're talking about m. We're talking about the change in y over change in x. We're talking about y2 minus y1 over x2 minus x1, right? That big thing. That's what we're talking about here when we talk about a derivative. We're kind of talking about the rate of change of a function, which is basically the slope. Okay, so let's say that you have f of x equals 3x. Okay, we want to know what the slope of this line is, okay? Well, you should be able to tell me right away, right? This is something you knew in algebra, right? The slope of the line is, of course, 3, right? That's m in that equation, right? So the slope of this line is 3, okay? That means, at any x, okay, at any x, you go up here, the change in y over the change in x is going to be 3, okay? So that's cool and all. And basically, that is your derivative. 3 is the derivative of 3x, okay? And let's kind of get more into that here. So let's graph that, all right? Let's graph basically y equals 3, but we're not going to say y. We're going to say y prime, and in this case, we'll write y prime. You know how y is usually represented as f of x? Well, we're going to write y prime equals f prime of x. Okay, so we're just going to write a prime to represent the derivative function. Okay, so we're going to graph this equation right here. F prime of x equals 3. Okay, so it's talking about so we have this graphed right here. Okay, that's basically y equals 3. Okay, and this function right here, this function right in front of you, this gives you the slope of y equals 3x. Right, that graph that we talked about up here. Okay, gives you the slope of that at any x value that you plug in. So I wrote myself another note here. Plug in 1 and plug in 2. So let's plug in x equals 1 here. Okay, so if we do f prime of 1, okay, we get, well, we're still going to get 3 because there's no like x's or anything like that over here. Okay, so f prime of 1 is 3. So that means that the slope of this line at x equals 1, right up here, the slope of this line at x equals 1 is going to be 3. Okay? Now what about at x equals 2? Well, f prime of 2 is going to equal 3 again, of course, right? Any x here is going to equal 3. Okay? And if you go up here, you get that the slope again is 3. Okay? So that's the idea. So now, of course, we already knew this stuff. Like, this already makes sense. I'm kind of just explaining it more towards so you understand the stuff later on with, like, you know, when we actually get into the real calculus. And this may seem rather unimportant to you right now. But what if we wanted to find the slope at any x for the function x squared? Well, this is different now because this isn't linear, right? We can't just graph this using y equals mx plus b, right? That's not how we're going to be able to do this. So how do we represent the slope at any x for this graph over here with another function? So what it turns out here is that this can be represented by the function y equals 2x. All right, and we're going to talk about how we get from, sorry, and this is actually y prime equals 2x. We're going to talk about how we get from y equals x squared to y prime equals 2x. All right, we're gonna talk about that, right? And the whole idea here is that this y prime equals 2x graph, okay? Let's plug in some points here, okay? Let's plug in, let me think here. Let's plug in, how about 0, okay? So if we have y prime equals 2x, okay, let's plug in 0. So if we plug in 0 for x, we should get that y prime at 0 equals 0, right? 2 times 0 is 0. So, well, is that, you know, and this is talking about the slope right here, right? Obviously, we can see that we can see that the y prime value at x equals 0 is 0, right? That's what this is telling us. So the slope of this graph over here at x equals 0 is going to be 0. It's going to be that y prime value on the other graph. Okay? So a little confusing at first, but let's do another one, get you to get the hang of this. What about y prime of 2? Okay, y prime of 2. Well, y prime of 2, we plug in 2 for x and we get 4. Okay, so if we go 2 up here, that means that this y prime value is going to be 4. All right, and what that means is that if you go to x equals 2 here, the slope of this graph at x equals 2 is going to be 4. All right, the instantaneous slope. That's what we're talking about here. That's why I have AKA the instantaneous slope. Okay, because you can't just talk about the slope of a graph anymore. Okay, because you know it doesn't have a constant slope. We're not going to be dealing with just linear functions. Okay, we're going to be talking about things that you know are parabolic, or maybe they're cubic, or things like that, and those aren't going to have a constant slope. Okay. So anyways, so that's the idea here. Okay, we get that the y prime value, okay, the derivative value on this graph equals the slope on this graph, okay, at that x. So now you know that we kind of understand what a derivative is, and trust me, we'll go back over this. So if it's confusing now, once we understand how to transform y equals x squared into y equals 2x, I'll go back and explain this over again, so it may make more sense to you then. Okay, anyways, talking about our derivative notation, how do we label our derivative function? Okay, now I already showed you y prime. That was something that we already kind of went over. Okay, so we'll write down y prime. But we can also write this as f prime of x, and this is also something that I mentioned. Okay, instead of f of x, right? That's what we would have labeled it before, as just our regular function. Now here's another one that we can label it as dy over dx. Okay, and you may have already saw this. If you've looked at, maybe you have an older sibling that's been through calculus and you see their paper and you got this dy over dx. Well, that's what that means. It means your derivative function. Okay, what's your derivative function up here? It's that y prime equals 2x. Okay, and you could have also wrote this as f prime of x equals 2x. You could have also wrote it as dy over dx equals 2x. All right, it all means the same thing. Okay, so when we transform a function to a derivative function, okay, so when we transform y equals x squared to y prime equals 2x, it's called taking the derivative. Okay, and in more like the bulk of the rest of the video, we're going to be talking about how you take the derivative. Okay, so we know to take the derivative if we see a d over dx. Okay, that's what's telling us to take the derivative. So if we want to take the derivative of this function over here, we have an example right here. Okay, and it's telling us we have y equals 3x. Well, if we want to take a derivative of this function, okay, what we do is this is just an operation, okay, and I'll talk to you about that in just a second here, but we do it on both sides. Like if we add something on both sides, we subtract something on both sides, we take the derivative of both sides. Okay, so we take the derivative of y, we take the derivative of 3x. Okay, and from that you'll get, and we talked about y equals 3x already today, so we're going to write y prime equals 3. Okay, and how I'll more refer to it is as f prime of x. That's the notation that I like the most. I don't really like the y prime stuff, but yeah. Anyways, so this is a operation. Okay, so this operation tells you to take a derivative, and since we have an x here, okay, it tells you to take a derivative with respect to x. Oops. All right. So with respect to x. So following that same logic, okay, if we had f of t, okay, if we had f of t, then if we took a derivative of that function, what notation would tell us to take a derivative of that function? It wouldn't be d over dx because we have a t, right? It's f of t. So it would be d over dt, right? So that's kind of the idea here. Okay, so getting more into that whole operation thing here, okay, if you were kind of confused about me mentioning operation, taking a derivative is an operation. Okay, just like addition, subtraction, multiplication, things like that. Right? So you can see an example of an operation. Addition is an operation, right? We have 3 plus 5, right? That plus sign tells us to add those two numbers, okay? 3 plus 5 equals 8. What about 5 minus 3? Again, you have that minus sign, okay? That tells you to subtract 3 from 5, okay? You get 2. And then you can multiply, right? So things like that, multiplication, okay? It tells you to multiply 5 and 3, you get 15. Okay, taking a derivative, okay, it's telling you to just, that d over dx, right? That's just telling you to take the derivative of 3x and you end up with 3, okay? So that's basically the whole idea. And how you would say this is kind of over here. That's what I wrote. You would say what this is as taking the derivative with respect to x, okay? So that's what this is, you're taking a derivative with respect to x of 3x. Okay? If it was d over dt, right? If we had a t here and we had a 3t, then you'd be taking a derivative with respect to t of 3t. All right? So that's the idea here. Okay? So now let's get into our first like how to take a derivative, our first rule that talks about all that stuff. Okay, we're going to talk about how we got from y equals 3x to y equals 3 without actually having to use that y equals mx plus b equation, and then we're going to talk about how we found we got from y equals x squared to y equals 2x. All right, so it's going to be pretty cool here. So how did we know that the derivative with respect to x of 3x equals 3? Now, as I said, it's fairly obvious when we graph it. It's fairly obvious when we use y equals mx plus b. But then what about that x squared graph that I showed you earlier? Okay, we have to use something called the power rule. Okay, now here's the power rule in its general form. Now, don't freak out. Okay, don't freak out. It's just, I'll go through it all. It's actually really simple. Okay, it says that the derivative with respect to x of x to the n, some power n, equals that power n times x to the, and your new power here is going to be n minus 1. Okay, so it looks kind of hard at face value, right? I set it out to try to make it sound a little bit easier, okay, rather than just saying d over dx of x to the n equals nx to the n minus 1, right? That sounds a lot harder than how I worded it, but you can still kind of make it seem a little bit better, right? It still kind of seems like what's going on here. So here's what this is really telling you. You have something like, so x squared, right? Well, what you're doing here, your n here, your n is 2. So since n equals 2 here, you have n, so you bring that power down and make it a coefficient in front of this x. Okay, and then you have this new power here, right? So you have n minus 1. So, well, 2 minus 1, right? Because remember, 2 is our n. It's 1. So we just lower the power by 1 and bring that previous power, which was 2, we bring it out in front of the x. Okay, so that's the idea here. And I believe I actually have an example of this below. So that's nice. But yeah, there you go. So what's the derivative of x squared? So as we said, right, we know that the derivative with respect to x of x squared is we're going to bring that power down in front of the x. So let's draw the x first. Okay, we bring this 2 down here, and then we lower the 2 by 1. So it's 2 minus 1. Okay, that equals 2x to the 1, which is just 2x, which is what we had before. Okay, so we bring that exponent in front of the x. Okay, we multiply it by that x, right? And we lower that power by 1. So let's do another one. What's the derivative of f of x equals 3x? Well, let's do power rule again here. We have we're taking the derivative with respect to x of 3x. Well, here, what's the power on x? Well, it's 1, right? It's the same thing as saying the derivative of 3x to the first power. Okay, and what we're going to do, the 3, that doesn't matter here, okay? That's just going to be left alone here. So what we're going to have is, actually, let's not write this. Let's leave this x here, okay? We have that first power up here, and we have the 3. We're going to take that 1, we're going to bring it down in front of the 3x, okay? So we take that 1, we bring it down, it goes right here. It's 1 times 3x. And up in the exponent, we have a 1 minus 0. Or sorry, 1 minus, 1, which gives us 0. So we end up with a 0 here. Okay, what's x to the 0? It's 1, so we get 1 times 3, which is 3. Okay, and that's how you can get the derivative function by actually taking a derivative for 3x instead of just graphing it. Okay, and it may seem here, okay, well, graphing is so much easier, I'm just going to do that. You can, but what if it asks you, okay, use power rule to take a derivative or things like that. So it's still good to learn this. Don't be a rebel in this case. All right, so now that we talked about power rule, okay, now that you hopefully are comfortable with this whole thing, all right, now let's move on to the properties of derivatives. Okay, so you've seen there that I was able to kind of leave this 3 alone, all right, and that's actually a property that we're going to be able to talk about here. Okay, so quickly, so you don't get confused, let's go over some properties of derivatives, and here I'm going to use c as a constant. Okay, so let's go over our first rule here, kind of our first property, and it's the constant rule. Okay, and the constant rule is exactly what we just did. or actually no, it's not. It's the next one is. Okay, so the constant rule says that if you take the derivative of a constant, okay, so of c, right? So if you take the derivative of 2 or 3 or 4 or 5, it's going to equal 0. Okay, why is it going to equal 0? Well, let's graph it and actually find out. Okay, so this actually will make sense to you. Well, if we have our axes here, okay, let's say we have y equals 3. Okay, if we have y equals 3 here, this is y equals 3. What's the slope of this line? Well, it's 0, right? It's 0. So our derivative graph is just going to be 0 for every x, right? So let's actually graph that one. So we graph our, well, this will be a y prime axis, this will be x. It's just going to be 0 for every x, right? But because remember, this graph over here gives us the slope at some x. Okay, so let's say we're talking about x equals 2. The y prime value is 0. The y prime value is the slope of this graph at x equals 2, okay, which is right here, which is the slope there is, of course, 0. All right, so that's the idea with the constant rule. What about the constant multiple rule? Now, this is what we were talking about earlier. The constant multiple rule says that if you're taking the derivative of c f of x, okay, so a constant in front of a function, like 3x or 2x, 3x squared, 4x squared, things like that, right, where you have that coefficient in front of some function of x, you can pull that constant out and kind of ignore it. So it's c f prime of x, right? We talked about how when we went from x squared to, or sorry, we went from 3x to just 3, right? We went from the kind of the actual derivative here was from x to the first power to 1x to the 0 power, which of course is just 1, right? That was the actual derivative, okay? But this 3 kind of just tagged along, right? So that's the idea here. Now what about the sum rule? Okay, the sum rule tells us that if we take a derivative, okay, of two functions that are being added together, okay, so if we have like, and I'll actually give you an example of this, but for now, this is f of x plus g of x, okay? This is actually going to be equal to f prime of x plus g prime of x, okay? So what this says is that you could take the derivative separately, okay? You can take the derivative of f of x and then just add it to the derivative of g of x, okay? So you get f prime of x plus g prime of x. And let me show you an example of what I mean. Okay, actually, do we do examples for this? Yeah, we do examples. So we'll actually see some here. But what I mean is like something like 2x squared plus 2x, right? You can take the derivative of 2x squared, and then you can take the derivative of 2x and just add them together. Okay, now the difference rule. Of course, the difference rule, as you can probably guess, is just the same thing. So you have f of x minus g of x. And when you take the derivative of that, you get f prime of x minus g prime of x. Okay, and then here's the do not do this rule. Okay, and we'll talk about how you actually do this later with product rule and quotient rule, but don't assume that since we can do this with addition and subtraction, that we can do this with multiplication and division. If you have the derivative with respect to x of f of x times g of x, this is not equal to f prime of x times g prime of x. Okay, as nice as that would be, that's not how this is going to work. Okay, and the same goes for division. Okay, the derivative with respect to x of f of x over g of x is not going to be equal to f prime of x over g prime of x. Okay, so if you're taking the, let's do a quick example of the do not do this rule. If you're taking the derivative of x squared over, we haven't talked about any other functions yet, but let's talk about x plus 1 or something like that, right? This is not going to be equal to the derivative of x squared, right? It's not going to be equal to 2x over, and we'll talk about the derivative of x plus 1 or something similar to that. The derivative of that is just going to be 1. Okay, it's not equal to 2x. This is not how that goes. Okay, so now that we've kind of talked about all the properties, right? We talked about the constant rule. The derivative of a constant is 0. We talked about the constant multiple rule. If a constant's out front of a function, if you have a coefficient, you just leave it alone. The sum rule, you can add two functions together and take the derivative. It's equivalent to the two functions by themselves when you take the derivative of it and add them. Okay, the difference rule, same thing but with subtraction, and the do not do this rule, multiplication and division don't work. Now let's do some examples of this. Let's take the derivative of f of x equals 2. Okay, so this is what rule is this? Well, this is rule number 1, right? This is the constant rule. Okay, if you just have that f of x equals 2, okay, let's imagine that graph is y equals 2 instead of y equals 3, right? The slope is still 0. So you can know that f prime of x equals 0. What about if f of x equals 2x squared plus 1 over x? Now don't get scared with that 1 over x. That's actually really simple. I'll show you that in a second here. But we can take the derivative of these things independently. F prime of x is going to equal, let's do power rule on this, right? This is 2x squared. This is going to follow power rule. We bring that 2 down, and we have 2 times 2, and that's going to be x to the, we subtract 1 from this exponent. You subtract 1 from 2, it's 1. Okay? And you're going to add, now here's the thing. We can rewrite 1 over x as x to the negative 1. Okay, it's the same thing, right? 1 over x is the same thing as x to the negative 1. So we can rewrite it like that. And now we can do power rule. This negative 1 goes in front of the exponent. So you have a negative 1 times x to the, you subtract 1 from this power, right? Which is going to be negative 2. Right? Negative 1 minus 1 is negative 2. So rewriting this to look a little bit nicer, we have f prime of x equals, this right here is just, that was an awful curly bracket. Oh my god. All right, that's just going to be 4x, right? X to the first is x. And we're going to be minus a x to the negative 2. We can rewrite that again as 4x minus 1 over x squared. Okay, and that's your derivative. Okay, moving on to our last example here. Okay, what if we have that f of x equals 3x cubed plus x squared minus 4x plus 1? Well, here it's going to be kind of the same thing. All right, the only difference here is now you have like a subtraction, but that's just, I mean, that's the difference rule, right? We can do the same thing as we did in the last example. So let's take a derivative of this 3x cubed here. Okay, take a derivative of this 3x cubed. We're going to bring that 3 down, put it in front of the 3x. Okay, so we have a 3 times 3x. Okay, we're going to lower the power by 1, so we get squared. Plus, taking the derivative of this now, x squared. This is where we bring the power down, get 2x, and you subtract 1, you get 1. Okay, hopefully this is starting to kind of catch on a little bit. All right, we go minus. We have a 4x to the first power. We bring that 1 in front, so we have 1 times 4. And then we have a x to the, subtract 1 from the exponent, 0. And then we have a 1, right? Remember, the derivative of a constant is 0. So we're actually just going to get plus 0. Making this look a little nicer here, we have f prime of x equals 9x squared. Okay, 3 times 3 is 9. Plus 2x minus, we have a x to the 0, that's just going to be 1, right? So we get minus 4. Okay, so pretty nice there. Okay, so hopefully that made some sense to you, right? If you're able to, and hopefully the power rule is kind of catching on with you. Okay, if not, maybe try one of these problems again on your own. See if you can understand. Okay, you move the exponent in front as a coefficient, and you subtract 1 from that exponent. Okay, and so you kind of, so if you have like x squared, you move that 2 in front. Okay, you move that 2 in front, and you subtract 1 from it, right? So out here it's 2, subtract 1 from this exponent up here. So you have 2x to the first power. Okay, that's the idea with the power rule. Now, if you're comfortable with the power rule, okay, it's going to make the rest of this lesson a lot easier. If you're not, okay, then I suggest you kind of go back and watch from the power rule again and start looking through this again, and hopefully it'll make a lot more sense to you now that you're kind of seeing it for the second time around. Okay, so moving on here, let's talk about some other derivatives. Now, there are some derivatives that these are some derivatives that don't, and I forgot to say, that don't follow power rule. All right, or they kind of have their own rule. All right, so just like for x to the n, right, that's where power rule comes in. But here, what if we don't have x to the n? What if we have e to the x? Or what if we have natural log of x, right? We don't use power rule for that necessarily, right? So they kind of have their own derivatives. And these kind of you just need to know by heart, okay? I mean, I could show you each of these graphs and show you how it's the slope, but I think it's just kind of easier just going to be to kind of go over these right now and hopefully kind of get some of these memorized real quick. So here's some common ones, here's some uncommon ones. Okay, we're going to go over the common ones first. These are the ones that are important, and the uncommon ones, we'll talk about those. But the derivative with respect to x of e to the x is just e to the x. It's the same thing, right? It's actually really nice. So the derivative of an exponential function is just going to be that exponential function, basically. And the derivative of natural log of x, okay, is just 1 over x. The reason why, that's going to make a little more sense when you get to integration, okay? So don't worry about that yet. But that derivative is good to know. Now getting into trig. The derivative of sine of x is cosine of x, okay? And the derivative of cosine is negative sine, okay? So it's kind of like a little circle here, okay? So the derivative of negative sine would be negative cosine. The derivative of negative cosine would be sine, okay? So it's kind of like just all revolves in a circle, okay? And actually, that's going to be really nice for kind of some stuff that you get into when you talk about Calc 2. But anyways, enough of that. The derivative of tangent x equals secant squared of x. Okay, the derivative of cotangent equals negative cosecant squared. Okay, so actually pretty similar to the tangent one, except it's negative now. Okay, and derivative of secant is secant tangent. The derivative of cosecant is negative cosecant cotangent. Okay, so again, these are actually pretty similar things. So if you kind of remember the secant one, it's kind of easy to remember the cosecant one. But now that all the common ones are out of the way, so e to the x, natural log of x, and all the trig, let's talk about some uncommon ones. Now, the first two here, the derivative of n to the x and log sub a of x, that you're not really, I don't think you'll really have to deal with too many of those, but if you do, these are the derivatives. So the derivative of n to the x is n to the x times natural log of x, and the derivative of log base a of x equals 1 over x times natural log of a. Okay, basically. And here is some derivatives that you may not really have to do in Calc 1, but they are going to show up quite a bit in Calc 2. So if you're reviewing this for Calc 2, these are some good derivatives to know. Okay, because now you're kind of expected to know a little bit more. And you go over these, but the derivative of the inverse sine is 1 over the square root of 1 minus x squared. You get the derivative of inverse cosine, which is negative 1 over the square root of 1 minus x squared. Derivative of inverse tangent, 1 over 1 plus x squared. Derivative of cotangent, inverse cotangent, is negative 1 over 1 plus x squared. Derivative of inverse secant is 1 over x square root of x squared minus 1. And the derivative of inverse cosecant is negative 1 over x times x, the square root of x squared minus 1. Okay, so hopefully I didn't overwhelm you there. I mean, those are just the uncommon ones. We're not going to focus on any of the uncommon ones. If you're in my Calculus 1 course, we're not going to do any of those derivatives. Okay, we're only going to focus on the common ones. So the common ones, e to the x. Okay, so an exponential. That's what that's called. I actually just learned that this year in I'm saying not linear algebra. And it doesn't matter, but I learned that this year. I didn't know that when I was in calculus, but you got e to the x, you got natural log of x, and you got trig. Okay, so those are the common ones that you want to know. All right. So now that we have that out of the way, let's get into our next rule for differentiation. So our next rule for taking derivatives. What if we don't have some nice polynomial? Okay. What if we don't have some nice polynomial like 2x squared plus 3x? Okay. What if we have two functions that are being multiplied? Okay, so for example, if you're taking the derivative of 2x times sine x, okay, well, and I'm not talking about, here's kind of like a non-example. I'll do like a little non-example quick. Okay, I'm not talking about if you're taking the derivative of 2x times x plus 1, because you could just multiply that 2x through. Okay, you could just say, oh, it's the same thing as taking the derivative of 2x squared plus 2x. Okay, and it is. So that doesn't really work for sine of x. You can't just multiply x and sine of x like you can with you can't distribute 2x through sine of x, if that makes any sense. Okay, so we need to use the product rule for this. That's long story short. Okay, and what the product rule says is that, and don't worry, I'm going to make this notation a little easier to see in a second here, but it says that the derivative with respect to x of two functions being multiplied together, f of x times g of x, is f prime of x times g of x. Okay, so the derivative of the first function times the second function plus the first function times the derivative of the second function. Now, this doesn't matter the order because of the commutative property, but that, you know, it's nice to do it in this order because that's going to matter for quotient rule. So going back to our example, let's point out which is f of x, which is g of x. Well, actually, let's do orange here. This 2 of x, okay, that's going to be, or sorry, 2x, that's going to be f of x. Okay, and sine of x, that's going to be g of x. Okay, so what the product rule tells us is that we're going to take the derivative of 2x, okay, and multiply it by sine x, and then we're going to take 2x and multiply it by the derivative of sine x. That's basically the idea here. Okay, and as a note, okay, this kind of goes with the properties that we discussed before. We can take that 2 out. Okay, so we can put the 2 on f of x, we can put it on g of x, or we can just pull it out completely. Okay, so we can just say the 2, we can say 2 times the derivative of x sine x. We can do that, okay, because it's being multiplied like that. So, you know, if you want to do that, that's fine. Okay, so, you know, this, hopefully the f's and g's aren't too confusing, but if they are, then here's a better way of writing this and making, and it's actually a lot easier to remember as well. So we can let u equal f of x, and we can let v equals g of x, just so you don't have all these parentheses going around everywhere and things like that. And we can rewrite the product rule like this. Okay, and we can say that the derivative, okay, of u times v is actually u prime v, so the derivative of u times v plus the derivative of v, so v prime, times u. Okay, that's a lot nicer than this mess. Okay, so if you want to write it like that, I definitely would advise it. Okay, so going back to the case before, so basically 2x would have been our u, okay, because u equals f of x, and then v would have been g of x, which is sine x. Okay, and let's do some examples of this. So let's actually take the derivative of 2x sine x. Okay, we already mentioned that our u is 2x. We said our v is sine of x. Okay, and remember that the product rule states that the derivative of uv is just u prime v plus v prime u. Okay, so and that I mean that's a lot nicer to say than the other one. But what's the derivative? What's u prime, right? What's the derivative of 2x? Well, that's just power rule, right? Bring that exponent in front. The exponent is 1, right? X to the first power. Bring that 1 in front. 1 times 2 is 2. And then you have x to the subtract 1 from that exponent, which is 1, and you get 0. So it's equal to, you can just say that this is actually 2. Okay, and then what about v prime? Well, what's the derivative of sine x? It's cosine x. Okay, and we already kind of mentioned that earlier when we talked about the other derivatives that we talk about. Now, taking the derivative of this now, we're going to get that f prime of x equals, we have a u prime, that's 2, times v, that's sine of x, and then we have plus v prime, which is cosine x. It's going to be times u, which is 2x. Okay, and then writing that a little bit nicer, we can say it's 2 sine x plus 2x cosine x. Okay, and that right there is your derivative. So that's just using product rule. Okay, now you can see where, if you don't understand power rule completely, okay, if you don't understand taking a derivative of x to some exponent, it's gonna affect you here. Okay, so if you're having trouble not seeing how I'm really taking these derivatives or things like that, I would go back to that power rule section again. Kind of go over that, make sure you're comfortable with everything there, and then product rule will be a lot easier, I promise. Let's do another example here. Let's do y equals e to the x tangent x. Okay, now here you can either label the derivative, you can label the derivative however you want. Okay, I'm going to label it now as dy over dx because we haven't used that notation yet. But let's talk about what u is. So u, we can see that we have two functions being multiplied. We have the e to the x and the tangent x. So we're going to say u equal to e to the x and v equal to tangent x. Okay, taking a derivative, that means u prime equals the derivative of e to the x is e to the x. Okay, and the derivative of tangent x, this one's you're not going to remember this one, but it's secant squared of x. Okay, so now we have u prime, we have v prime, we have u and v, we can substitute in. Remember, okay, the derivative is going to be u prime v plus v prime u. Okay, so it's going to equal u prime v plus v prime u. Okay, which here is going to be u prime is e to the x. We have v tangent x plus v prime, that's secant squared x, and we have u is e to the x. So actually I'm going to write it like this, just for consistency. Okay, so, and you can also take an e to the x out here and say tangent x plus secant squared x. It's up to you. You don't have to do that. It may make it look a little nicer. Here, it looks a little bit nicer, I guess, but so yeah. All right, so let's do another example here. And real quick, if you can try this one on your own, I think that would help you a little bit more. Try this one on your own, okay? And whether you can get it or you can't get it, I'll still be going over this with you guys, so it's okay regardless. But I think that if you try it on your own and it's not just me doing it, right, that's going to help you a lot more than if it was just me talking at you, okay? So, and you can also see the problems that you're having yourself. So anyways, assuming you've tried the problem, let's start here. We have that f of x equals x squared plus 1 times cosine x. Okay, now something you could have done, you could have multiplied that cosine x through to the x squared and the 1, but you could have also said, and probably the better way of doing this is that u equals x squared plus 1 and v equals cosine x. All right, so there's your two functions. Okay, u prime, taking the derivative of this, let's see if you can follow this here, just going to be 2x, right? We already talked about the derivative of x squared, that's 2x, right? And we talked about the derivative of a constant, 1, 2, 3, 4, 5, whatever, negative 1, negative 2, it's 0, okay? So derivative of and a constant is 0. So we just get 2x. And the derivative of cosine x, if you remember from before, it's negative sine x. Okay, so now we can plug this into the product rule. The product rule tells us that the derivative is going to be u prime v plus v prime u, which, when we plug that in, we get 2x, that's u prime, times v, which is cosine x, plus v prime, that is negative sine x, and that's going to be multiplied by u, which is x squared plus 1. So we can rewrite this as f prime of x equals 2x cosine x minus a x squared plus 1. I just like to put the function, the polynomials before the trig functions, and then you have sine x. Okay, so that is your derivative. Okay, so really, if you can find what your u and v is, right? You see the two separate functions there. So if you have, for instance, here, you have x squared plus 1, you have cosine x. Okay, you know that x squared plus 1, that's its own thing. You have cosine x, that's its own thing, right? Those are your two functions, so you know you're using product rule. You label one as u, one as v, you take derivatives of them, and then you just plug it into the formula. Okay, that's all you're really doing here. And then it's basically just algebra. Okay, so there's not too much actual there's not too much of the calculus part of what you're doing, right? It's very small. It's just basically plugging into, it's taking derivatives. That's the calculus part. Okay, and then it's just algebra to simplify everything. Okay, so let's move on to the quotient rule. Okay, so what if we have two functions that are being divided? So we have something like e to the x over x. Okay, so you have two different functions. There's no way to combine these two. Okay, there is a way to combine x squared over x, which is kind of our non-example over here. You can just write this as x. So you can take a derivative using power rule, right? A lot easier. Okay, so we're going to have to use the quotient rule here. Okay, and the quotient rule states that, and don't get confused with all this notation, I'll be going over this, we'll understand it. All right, so just don't get overwhelmed right away. The derivative of, we're going to call f of x the top function, we're going to call g of x the bottom function, instead of the first and second, because I feel like top and bottom makes a little more sense here. So it equals the derivative of the top function times the bottom function minus the derivative of the bottom function times the top function, and that's all over the bottom function squared. Okay, and basically right here, this is just product rule. Okay, that line that I just highlighted, that's product rule, except now we have a minus. That's the only difference. Okay, so and to see that even more, let's set u equal to f of x again, and we'll set v equal to g of x. So we're going to actually see this here. Okay, and we get that the derivative with respect to x of u divided by v equals u prime v minus v prime u. Okay, so instead of product rule, right, was u prime v plus v prime u. Now it's u prime v minus v prime u. Okay, and it's over v squared. Okay, so in v squared, that's just this thing squared. All right, so here's a great way to remember this. I know actually pretty much everybody I talk to about calculus remembers it this way, so I definitely want to teach it here, because I feel like this will if you're not really happy with the way I'm saying, u prime v plus v prime u or things like that, here's a better way of remembering this. Okay, this is low d high minus high d low over low squared. Okay, low meaning of course the bottom function, high meaning the top function, and when you say d, it just means derivative. Okay, so what this means, low d high, means you're multiplying its low times the derivative of the high function minus the high function times the derivative of the low function over the low function squared. Okay, so I feel like maybe that'll be a better way of remembering it. I know a lot of people just say low d high minus high d low over low squared. Okay, and they say it really fast like that. Okay, and that's how they remember it. Okay, in our examples, of course, I'm going to be giving you the formula again because I don't expect you to remember it in 2 seconds. Okay, that's not how this works. All right, and that's why, and I don't expect you to remember the other derivatives that we talked about either in this video right away. Okay, it's going to take some time. It's going to take some practice. It's going to take a little bit of conceptual work too. So, anyways, let's keep moving. So let's do an example. Let's take a derivative of that function that I just mentioned, e to the x over x. Okay, remember that the quotient rule says that we have the derivative of u over v equals u prime v minus v prime u over v squared. And we just got to find what u and v are now. Okay, so where am I going to write this here? Let's write it over here. So, and I'll write it in a different color to make it distinct from the other stuff. U is going to equal our top function. It's going to equal e to the x. V is going to equal our bottom function. It's going to equal x. So u prime, the derivative of e to the x is e to the x. Okay, we've talked about that a couple times in this video. And the derivative of x, you move that 1 in the exponent. Actually, I should probably go down on the screen here. You have 1, and you multiply that 1 in front of the x, so you get just 1 x to the, and this you subtract 1 from the exponent, you get 0. So you have v prime equals 1x to the 0, which is just 1, basically. Okay, x to the 0 is 1. So now you're all ready to plug in. Okay, you get that f prime of x equals u prime v, okay, e to the x times v, which is x, minus v prime, that's 1, times u, e to the x, over v squared. V squared, you're talking about x here, that's v, so we square that, we get x squared. And rewriting that to look a little nicer, we get x e to the x minus e to the x over x squared. Okay, so, not too hard, okay? Again, just taking derivatives, plugging into a formula. If you can find if you can figure out that you're going to use the quotient rule because you have a fraction, you have a function on the top, a function on the bottom, you can't simplify it at all, you use the quotient rule, all right? You take a derivative of the top function, take a derivative of the bottom function, and plug into the formula, right? That's what the quotient rule is, okay? So taking 2 derivatives and then putting into a formula. That's it, right? And doing some algebra work to simplify it, okay? So, it's not terribly difficult. It's definitely tedious because it's a bigger formula than the product rule, and that's why I think a lot of people don't like it, me included. But the reason why that I would rather do something else is because you can just do product rule. Okay, and that's a note that I have here. We could have just used product rule for this because we could have wrote this as f of x equals e to the x times x to the negative 1, right? This is the same thing as saying x to the negative 1 times e to the x, because you can put that x up to the top by writing x to the negative 1. So we can write it like that, and that's how I used to do it because I didn't like quotient rule. Sometimes I just do quotient rule now. I don't really care too much anymore, but enough about the story of my life. Now let's get on to our next example here. So we have f of x equals 2 cosine x over 3 tangent x. Okay, and here's the thing with this example. We could break this down into sines and cosines. So we have a tangent there. We could say sine over cosine, right? And that would actually be a little bit better to do here because our answer is just going to look a little bit nicer. Okay, but what we're going to do here is just do quotient rule anyway. I'm going to show you how kind of gross our answer looks and why it might be nice to break this down into sines and cosines the next time we see something like this. Okay, so the idea is we have 2 trig functions. We have 2 cosine x, we have 3 tangent x. Okay, and what we can do here is say that u is equal to, let's actually just say that u is equal to cosine x. Let's worry about that too some other time. Okay, let's set v equal to tangent x. In which case, u prime is the derivative of cosine x, which is negative sine of x, and v prime is the derivative of tangent x, which is secant squared of x. Okay. Again, if you don't memorize these, if you don't have these memorized right now, at least, don't freak out. Okay. No big deal. Just know that this is the derivative of that. Okay. That's kind of the idea. So, and remember our formula is that the derivative of u over v is u prime v minus v prime u over v squared. All right. Plugging in here, we get that f prime of x equals, we're going to put a 2 over 3 right here because that's where this is coming from. Okay, so 2 over 3 times, it's going to be u prime, that's negative sine of x, times v, which is tangent x, minus v prime, secant squared x, and u, which is cosine x. And that's going to be all over v squared. V is tangent, so it's going to be tangent squared x. Okay, now this is pretty much, I mean, that's pretty much all you can do with this thing. I mean, you can definitely do some more stuff, but you know, by breaking down into sines and cosines. But honestly, this is I'm not going to do that because I don't want to. That's actually why. But you know, if we broke this down into sines and cosines, then here's what happens. And we have that f of x. Instead, we have a 2 cosine x over 3. We have a tangent. So actually, instead of a tangent, we can write this as sine x divided by cosine x. Okay, in which case we would have a 2 cosine squared x over 3 sine x. And, well, actually, this may not be a great example of something that you'd want to break it down in sines and cosines and go through, but and we'll talk about how to integrate or to take a derivative of cosine squared. But you know, you definitely want to look to that first, is what I would do. Okay, because maybe instead of having a cosine squared over sine, which actually may not be the best by itself, we could have canceled out cosine and just had like a sine on top or something like that. You know, if we had something like that, it's a lot better. So what I would, you know, maybe while this is not a great example, I would say that you should break down into sines and cosines first. Okay, so anyways, so let's move on to our next example. That was a fail. So we have y equals x over x squared plus 1, and you can try this on your own. Okay, just help you out a little bit more. Our top function is x. Our bottom function is x squared plus 1, and u prime is 1 because the derivative of x is 1. And our derivative of our bottom function is just going to be, well, the derivative of x squared, again, is 2x. Derivative of 1 is 0, so 2x plus 0, which is just the same thing as saying 2x. Okay, and remember our quotient rule, right? We have u prime v minus v prime u over v squared. Okay, and now we're just plugging in. All right, so my x, that's my top function, so that's u. My x squared plus 1, that's my bottom function, that's v. We take derivatives to get u prime and v prime, and we plug into this formula. That's literally all we have to do for this. Okay, so u prime, that's 1. Okay, so we're going to say dy over dx. Okay, and actually notice how this works here. If we're taking a derivative of y, okay, that is dy over dx. That's where that notation comes from. Okay, kind of cool, right? So it's kind of like you're multiplying that y to the d, essentially. I mean, that's how you can think about it. So anyways, u prime, that's 1. V is x squared plus 1. You have minus v prime is 2x, and u is x. And we're going to divide by v squared, which is x squared plus 1, and we're going to, of course, like I said, we have to square that. So we get x squared plus 1 quantity squared. Okay, so simplifying this, we can get x squared plus 1 minus 2x squared okay? And we put that over x squared plus 1 squared. So we can again simplify this to say this will be a negative x squared plus 1 on the top, combining like terms. And we have a x squared plus 1 quantity squared on the bottom. And what we can do actually is, well, we can't. No. I almost did something bad. Okay, no, we're going to leave it like this. We can't substitute out that negative and then cancel out an x squared plus 1. That's what I was about to do. And you can't do that because this negative is only on the x squared. It's not on the 1. Okay, so don't do that. All right, so now what we're going to do is we're going to move on to chain rule. Okay, now chain rule is really nice, and you're going to be using it in pretty much, I mean, I would say the majority of the derivatives that you see, or the derivatives that you have to take. Okay, and it can get a little complex, so just try to stay with me here. You might have to watch this back again, okay, but I'm going to go slow. I'm going to try to just make sure that I talk about each thing thoroughly so it's easy to understand. Okay, here's chain rule. So we have, this one more rule left, okay, and this one is used more than the last two. It's definitely used more than product rule and quotient rule. What if we have a function inside of a function? Okay, like Inception. All right, we have something like cosine of 2x, where this 2x is inside of cosine. What about we have x squared plus 1 quantity to the 4th power? Okay, where we have x squared plus 1, this whole function being taken to the 4th power. Okay, you can kind of think of that something to the 4th power as like the outside function. Okay, and x squared plus 1 is on the inside. And what if we had instead of being e to the x, we have e to the 4x plus 4. Okay, so 4x plus 4 is that inside function in the exponential. Okay, so we have to use something called the chain rule here. Okay, and this notation may seem a little weird, but it's actually a lot easier in practice than the notation makes it seem like. Okay, so we got to use the chain rule. And what this says is that if you have a function inside a function, that's what f of g of x means. You have a function inside of a function. This is equal to f prime of g of x. So you take the derivative of that outside function, just like you normally would, but then you multiply by the derivative of the inside function. Okay, so this may be really confusing to look at. So let's look at one of the examples that we talked about from above. We talk about y equals cosine of 2x. All right, well, in this case, okay, the whole thing is basically the outside function, or more specifically, I guess you could say that cosine. Okay, cosine is the outside function. Okay, and if you want to think of it as just the whole thing is the outside function, absolutely go for it. That's fine. Whatever kind of makes the most sense to you. What's the inside function? Well, it's what's inside cosine, right? What's inside cosine? That's 2x. 2x is inside the cosine. So 2x is the inside function. Okay, so basically what we do here, okay, we're going to take the derivative of cosine of 2x as we normally would, and for some reason that doesn't have a y there. Oops. So we're going to take the derivative of cosine of 2x as we normally would. So, what's the derivative of cosine of x? It's negative sine of x, right? So the derivative of cosine of 2x, we're going to write that as negative sine of, instead of x, we're going to write 2x. But here's what we're going to do instead. Okay, we're going to multiply that negative sine of 2x by the derivative of the inside function. So, but now we multiply by the derivative of 2x. Okay, so let's do some examples of that. Let's just jump in here. Okay, we talk about, we're gonna start off right off with that cosine of 2x. Okay, so remember what the chain rule says. We're going to say that the derivative of f of g of x equals f prime of g of x times g prime of x. The first thing we got to figure out is what is f prime of g of x, and I already kind of said it earlier. Okay, the derivative of cosine is negative sine, and we keep that g of x in there. Okay, that's basically what we're doing, right? F prime, so we take the derivative of that outside, we take the derivative of cosine, but then we kind of just leave that 2x in there. Okay, that 2x kind of stays put. Okay, so whereas the derivative of cosine of 2x, sorry, the derivative of cosine of x would be negative sine of x, we now have that the derivative of cosine of 2x is going to be negative sine of 2x, and then we're going to multiply by g prime of x. Okay, g prime of x is the derivative of the inside, the derivative of 2x. Okay, now try to think, what's that derivative of 2x going to be? Well, according to the power rule, it's just going to be 2. Okay, just going to be 2. Here's why. We have 2x to the first power. We move this 1 in front. Okay, so we have 1 times 2. X to the, we subtract 1 from that power, we have 0. Okay, so it's going to be 1 times 2x to the 0. So 1 times 2, that's 2. Okay, so we can write equals 2. All right, so we just multiply these two things together now, and we have our derivative. We have dy over dx equals negative 2 sine of 2x. All right, so that's basically it for that one. So let's move on to our next example. We have y equals and this is actually the same example we had from before, again, as is letter C, but it's x squared plus 1 quantity to the 4th power. Okay, so what do we end up doing here? Well, it's a little bit harder to see what the inside function is, okay? Or sorry, what the outside function is. I mean, and here's kind of where it's a lot nicer to just kind of view it as, actually, maybe here's a better way of viewing it. I hope if this confuses you, just forget this completely. But what you can view this as is, you can say let's say b equal x squared plus 1. Okay, if you let b equal x squared plus 1, then you just have b to the 4th power. Okay, if you take a derivative of b to the 4th, it's just going to be 4b to the 3rd power, right? So you just do power rule. Okay, and if you plug in back the x squared plus 1, it's 4 times x squared plus 1 to the 3rd power. Okay, and of course you have to multiply by the derivative of the inside, but that's kind of what I mean by just taking the derivative of the outside function. Okay, so if that didn't make sense to you, just kind of forget it, but I just wanted to try to communicate that a little bit better. Okay, so we start off by taking the derivative of that outside function, and like we just said, it's going to be 4. Okay, we move the 4 to the front, we multiply it, right? And we subtract 1 from that 4, put it in the exponent. Okay, so then we multiply by the derivative of the inside. The inside is x squared plus 1. We've actually done this derivative quite a few times in this video already. The derivative of x squared plus 1 is just 2x. Okay, so making that look a little bit nicer, we have 8x times x squared plus 1 to the 3rd power. Now you might be asking, well, why couldn't I just multiply x squared plus 1 out by itself 4 times and then just take the derivative and that would just be power rule, right? Because you just have a little string of just like, it'd be a polynomial. It'd be a pretty long polynomial, but it'd just be a polynomial. And you can do that. You absolutely can. And actually, one kid in my class that did that. He just wanted to do that, and then the teacher gave him something to the 7th power instead, so he didn't do that anymore. But anyways, the reason why is because this does not take as much time. We just took that derivative in pretty much no time at all, right? We didn't have to multiply x squared plus 1 out 4 times and then take a derivative on top of that. Okay, it's a lot more work compared to just a little bit from knowing chain rule, and you're going to need to know chain rule for other things too. Okay, so it's a smarter decision. So that's our derivative, just x, or 8x times x squared plus 1 to the third power. So let's move on to our last one here. We have y equals e to the 4x plus 4. What's going to be our derivative of just the outside function? Well, the derivative of e to the x, okay, if you differentiate e to the x, it's just e to the x. Okay, so our outside function, right, this is just going to be e to the 4x plus 4, right? We're going to leave this alone. And then we multiply by the derivative of the inside function. What's inside? Well, we have this 4x plus 4 up here instead of x. Okay, and we just end up getting, sorry, not e. The derivative of 4x plus 4 is just 4. Why? Well, 4x plus 4, you have a 1 in the exponent on x here. Move this out to the front. This becomes a 0. Okay, so you just have 4, and then you have plus. This is a constant, so it goes to 0. So you just get 4. Okay, so that's a derivative real quick of that. And you get 4e to the 4x plus 4. That is the derivative via the chain rule. Okay, so hopefully it seems pretty simple here, right? Hopefully you're not getting too confused with the inside function, outside function terms. I think that's maybe what I got caught up on when I was in calculus 1 doing chain rule. But if you can kind of get past that, you see that the 4x plus 4, is where that x would usually be. That's kind of what we're going to treat as our inside function. Our outside function is just that e to the 4x plus 4, essentially, right? That's the whole function. What's inside of that, it's that 4x plus 4. Okay, so we have to take a derivative of that. Now, we're gonna show some consistency here in our note. Okay, what if we're taking the derivative of sine x? Okay, take the derivative of sine x. Okay, remember this means taking a derivative with respect to x of. Okay, and then we just have sine x. So remember that the derivative of sine x is just cosine x, right? But what's that inside function? Okay, well, the inside function would just be x in this case. Like if there's a 2x, the inside function is 2x. If there's a 4x, the inside function is just what, of course it's whatever is inside that trig function. Okay, so we have to take a derivative of that. So why didn't we, when we were just talking about our other derivatives, we were talking about power rule, why didn't we do any of that stuff? Well, because if you just have an x, what's the derivative of x? X to the first power, you move the 1 here, and you get 1x. You subtract 1 from the exponent, you get 0. So this is just 1. And you multiply anything by 1, it's just going to be that thing. So we don't need to do chain rule for everything. We're essentially doing it, right? But multiplying by 1 isn't going to change anything. So we only need to do chain rule when we have something that's other than x, in an exponential or inside a trig function, or we have a polynomial being taken to a very high power, things like that, right? So let's do some quick review. Okay, I know we've went over a lot of things, and I hope you're not too overwhelmed right now, but this is a lot of information. I think this is, depending on your calculus class, this is 1 week to maybe as far as a month of calculus. I don't know exactly if it'd be a month, but it's a lot of calculus that we just went over. Okay, so let's do a quick review. Let's kind of just put everything, let's make everything concrete. Okay, so what are these new functions f prime of x and dy of dx that we're finding? Okay, what are these actually representing? Okay, well, in these functions, and before I actually write this down, why don't you try telling me? Okay, if you're in front of people, just just say it in your head. Okay, you don't gotta go saying it out loud or anything. But what are we actually finding here? Let me know if you can think of it first. Okay, so assuming that you've tried in these functions, you input an x. Okay, and what are you outputting? Your output is the slope of the original curve. At that x value. I think that's the most crucial thing. Okay, it's at that x value. So if we have that, we have f of x equals x squared. We take a derivative of x squared, we get 2x. Okay, we've been over that 100 times in this video. Okay, if we plugged in, if we wanted to find the slope of this graph at x equals 2, our derivative is going to tell us that. Okay, because what we can just do is plug in 2 for x, and we get 2 times 2, which is 4. So that means that the slope of this graph at x equals 2, the instantaneous slope rather, because of course the slope is changing for every x, it's 4. Okay, and there's a lot of applications for this. Okay, we're not just doing it to mess around with all this slope stuff, right? Rate of change is very significant, right, in physics and of course calculus, because that's what it's based on. But that's kind of what we're doing here. Okay, so we're going to we're going to plug in x equals 3 to the derivative equation. We just plugged into right here, but if we plugged in 3, let's just do another example here. Plug in 3, we get 2, or sorry, yes, it's going to be 2 times 3 now, because we just have 2x, right? So again, originally we had f prime of x equals 2x. We plug in 3 for x, we have 2 times 3, that's 6. So the slope of this curve at x equals 3, and if I drew it tall enough, there you go. The slope right here is 6. Okay, going 6 units up and 1 unit over. That's the idea. So how do we transform these functions into their derivatives? Well, we use a bunch of different rules, okay? And of course we have some other derivatives too, like e to the x, natural log of x, and the trig functions, things like that. But there are some rules that we use for just pretty much everything else. Or sorry, the power rule. Let me rephrase that actually. The power rule is what we use for things that are like x to the n, or you have like a polynomial, things like that. But if you have e to the x, natural log of x, or a trig function, then you use it like kind of its own rule, I guess. And then product rule, chain rule, quotient rule, that applies to everything. Okay, sorry, I kind of messed that up for a second there, but I'm not going to cut it out because YOLO. So take a derivative of x to the n, that's n to the x, n times x to the n minus 1. And if you took a derivative of two functions being multiplied together, one function u, one function v, okay, well these are just both functions of x, like u is 2x and v is e to the x, something like that. Your derivative is u prime v plus v prime u. If you do the quotient rule, instead you have u divided by v. You have u prime v minus v prime u over v squared. Remember, low d high minus high d low over low squared. Okay, you can remember it like that too. And the chain rule, this one's kind of harder to look at. But if you have the derivative, if you're taking the derivative of f of g of x, it's equal to f prime of g of x times g prime of x. Okay, so those are your 4 rules that you're going to be using a ton when taking derivatives, right? That's how you take derivatives, is you use these rules. Okay, so and I talked already about their functions that have their own rules, like e to the x, natural log of x, and trig. So instead of using power rule, actually this is exactly what I was saying before. So you still have e to the x, natural log of x, and trig functions that have their own rules instead of power rule, but these still work with product, quotient, and chain rule. Okay, so now let's move on to some practice. Okay, and try to do as many of these as you can. And so it's not just me talking at you, like I kind of mentioned before. All right, it's definitely going to be more beneficial for you if you try these on your own first. Okay, but without further ado, let's hop into this, and you can just pause the video whenever you like. Let's take the derivatives of the following functions. Let's first take the derivative of 1 over x squared. Now, if you immediately go, oh my god, I have no idea, well, it's probably because you're not recognizing that 1 over x squared is the same thing as x to the negative 2. Okay? If we take a derivative of x to the negative 2, it's just a simple application of the power rule, right? So we move that negative 2 down in front of the x, and we subtract 1 from the exponent, which gives us negative 3. So we can rewrite this as negative 2 over x cubed. And that's your derivative. Okay, so that's the first example. All right, so just real quick, and I know that my teacher, she would assign a lot of questions like that, like 1 over x cubed, and a lot of students would get stumped because they didn't realize that 1 over x squared is the same thing as x to the negative 2, and that is just a simple power rule application. Okay, so just recognizing that, I think, is really big. So that's why I wanted to do another example of that. On to number 2. We have that a function of x equals x squared times secant of x. Okay, so here, what rule are we going to use here? Well, we have two different functions being multiplied together. We have x squared, and we have secant of x. Okay, so one's going to be our u, and one's going to be our v. Let's set u equal to x squared and v equal to secant of x. Now we're going to have u prime. Well, that's just going to be the derivative of x squared. Again, that's 2x. All right? And the derivative of secant x is secant x tangent x. Again, you don't need to remember that right now, but that's just what the derivative is. Okay? So f prime of x is going to be equal to, remember our formula, it's u prime v plus v prime u. And I guess real quick, how you can kind of remember that, how product rule is plus and quotient rule is minus, is because nobody likes quotient rule and nobody likes negatives. So that's why quotient rule has a negative, because nobody likes it and nobody already likes negatives. So yeah. All right, so enough of that. U prime is 2x. We have v, that is secant of x. And we add v prime is secant x tangent x. And we multiply by u, which is x squared. So rewriting this again to look a little bit better, we get f prime of x is equal to 2x secant x plus x squared times secant x tangent x. So now let's move on to number 3 here. And we have that f of x equals sine x over x. Okay, so what rule are we going to use here? Well, we have a function divided by a function. Okay, so probably quotient rule, right? So our top function, and we can't simplify this at all, so if we could, then we would. We have sine x over x, right? So our top function, that's going to be u, and our bottom function is going to be v. So u prime, derivative of sine is cosine, and the derivative of x is 1. Okay, again, if you're nervous on the whole derivative of x thing, move the 1 in front, so you get 1x, and you subtract 1 from this 1 here. So you have 1 minus 1 in the exponent, and you get 1x to the 0, which is just 1. Okay, so hopefully you're not still confused with the power rule stuff. Anyways, we can write out what a quotient rule says. It's u prime v minus v prime u over v squared. And we have u prime v, so that's cosine x is u prime, and v is x. And it's going to be minus v prime, which is 1, times sine x, which is u. And that's going to be all over v squared. V is x, so it's going to be x squared. And simplifying this, it's going to be x cosine x minus sine x all over x squared. Okay, so we were able to get that, right? And that was fairly simple. But let's say that you're in the middle of a test and you forget what quotient rule is. Well, we can actually use product rule for this problem. So let's try and do that quick. Okay, I know there's a lot of students that forget quotient rule. I think I've probably forgot it once or twice doing this stuff. So, sometimes I just use product rule. So our function of x is sine x over x. So we can rewrite this as x to the negative 1 times sine of x. And in this case, now we just use product rule. Okay, we have two functions being multiplied together. So x to the negative 1 is going to be our u, and sine x is going to be our v. Okay, so we have u equals x to the negative 1, v equals sine x, and u prime. This is going to be a little bit tougher. And actually, this is a derivative I really like to memorize. I knew we were always using this thing, the derivative of 1 over x. Okay, it's derivative of this thing is negative 1 over x squared. I like to remember that, but I'm not expecting you to right now. Here's how you do the derivative of x to the negative 1. Okay, well, it's just power rule. So we bring that negative 1 in front, and we subtract 1 from the exponent. Okay, so we have basically negative x to the negative 2, which is the same thing as negative 1 over x squared. Okay, so that's how you get that. We can write that as negative x to the negative 2 for now, just because we're still writing negative exponents. And we have v prime, that's going to be cosine x. That's the derivative of sine. Awesome. So now, what's our product rule? It's u prime v plus v prime u. And u prime is negative x to the negative 2. We're going to multiply v, which is sine x. And now we have plus v prime, that's cosine x. And u is just x to the negative 1. So now we have our derivative, but it doesn't really look the same as our other one, which is x cosine x minus sine x over x squared, right? This looks a little bit different, but we also have negative exponents here, and these are the same thing. Okay, this is the same thing as this, but I want to show that in full so you actually believe me here. Okay, we're going to rewrite this without the negative exponents, and we're going to flip around these two terms just using the commutative property, right? So we'll have a 1 over x times cosine x. Okay, that's this piece over here, and rewritten with the negative exponent as just a positive exponent. And then we're going to write this one over here. So it's minus 1 over x squared times sine of x. Now here's how you can rewrite this. Since there's an x in both of these denominators, you can rewrite it as f prime of x equals cosine of x minus 1 over x sine x over x. And let's see now how close we are to our regular one. Well, here we have x cosine x, so we only have a cosine x here. And we have a 1 over x sine x rather than a sine x, and we have an x rather than an x squared. If you can spot the difference here, then you're good. Okay, but basically we have to multiply by x over x. Okay, we multiply top and bottom by x, and we get x cosine x minus sine x over x squared. And that is what we had up here. Okay, so these are the same thing. You can use product rule for this. And, it took, you can leave it with the negative exponents if your instructor is okay with that. I definitely would ask first, because, each instructor kind of has their different idea of what simplified is. And some people don't care at all if you simplify it, so I would talk to them. But you can see here that if you forget quotient rule during the middle of a test, it's not the end of the world. You can just use product rule. And you can honestly, let's say you somehow remembered quotient rule instead of product rule, you can just, use quotient rule for a product rule problem by flipping an x or something like that, but I would never do that ever. Okay, I'm just letting you know that you can use these rules interchangeably by manipulating the function a little bit. So here's another function. We have x cubed plus 2x squared plus 1. That's all being raised to the 6th. Now you wouldn't want to multiply this thing out 6 times, right? So we're going to have to use chain rule. Okay, let's take the derivative of this function as we normally would if it was like x to the sixth. So we're going to have 6 times x cubed plus 2x squared plus 1 to the fifth. Okay, we just drop the exponent by 1. And then we multiply by the derivative of the inside function. Okay, so the derivative of the inside function, let's see if you can follow me here, is going to be 3x squared plus 4x plus, it'll just be 0, so we're just going to end that off here. So f prime of x equals, we can multiply through, okay, we get 18x squared plus 24x, and we multiply that by x cubed plus 2x squared plus 1 to the fifth. Okay, so that actually let's go over that derivative again quick, just in case you didn't get how I got this thing. The derivative of x cubed, move that 3 out front, drop the exponent by 1, you get 3x squared. For 2x squared, multiply that 2 by the 2 already out front, you get 4x, and then you have to lower the exponent by 1 of 2, so you get 1. Okay, so 4x to the first power, that's just 4x. So that's how we did all our derivatives there. Now next, we have sine cubed of x. Okay, this is the same thing as saying sine of x, and that quantity is being cubed. Okay, so we can just kind of take the derivative normally as if we were taking it as like x to the, or x cubed. So we can say that f prime of x is equal to 3 sine of x squared. Okay, and I think that's actually the best way of wording that. I know I was kind of struggling with that earlier, how to really just hone in on what chain rule is actually telling you. I think that's a good way to phrase it. You're just kind of taking a derivative as if it's x to the third power instead of sine x to the third power. Okay, so you're just kind of, it's like using power rule basically, or it is. So now we have 3 sine x squared, but we have to multiply by the derivative of the inside, which is cosine x, right? Derivative of sine x is cosine x. So we can rewrite this as f prime of x equals 3 sine squared x cosine x. All right, so that is your derivative function. All right, let's move on to our 6th problem. Hopefully you're starting to get comfortable with these things here. Okay, and just if you really start to think you are getting comfortable with this stuff, I'm going to throw a couple curveballs at you here. So let's see what you got. All right, what you're really made of here. Let's do f of x equals x squared plus 2x plus 2. That's going to be raised to the 5th power, and you're going to put that over x. So here, what are we going to have to do here? Well, we have a function over a function basically. So this is quotient rule. Okay, we have our top function, and we have our bottom function. The only difference is now we're going to have to use the chain rule for the top function. And that's the kind of kick to this problem, or the hardest part about this problem. Okay, so v is going to equal x. So what's the derivative of u? Well, u prime is going to equal, remember, we take the derivative of this thing as if it was just x to the 5th. So it's 5 times x squared plus 2x plus 2, and that's all raised to the 4th now. And then we're just going to multiply by the derivative of the inside, so 2x plus 2. Where did I get that from? Well, the derivative of x squared is 2x, and the derivative of 2x is 2. Okay, hopefully you're comfortable with power rule by now. Okay, because we've had to do it a ton. All right, so, and of course the derivative of x is 1. So now let's use our quotient rule here. We know that our quotient rule is telling us f prime of x is going to equal u prime v minus v prime u over v squared. And now we plug in with our insane u and u prime and things of that sort. So we're going to have to start with u prime. Now I would simplify this with the 2x and the 2x plus 2 and the 5. So I'd multiply the 5 through to the 2x plus 2. And when you do that, you get 10x plus 10. And you multiply that by, of course, your inside there. That's 2x or x squared plus 2x plus 2 to the 4th power. So multiply that by x. And you subtract, we're not going to have enough room here. Let's do this. Okay. We're going to subtract v prime, which is 1. And then we have u, which is x squared plus 2x plus 2 to the 5th power, over v squared, which is x squared. All right, so that's basically it. Now we can simplify this here. I'm not going to simplify this. I don't want to. This video is long. Not doing it. All right. So you understand. We went through the good part, which was taking a derivative. All right. Now what about this one? This is interesting. We have tangent squared of 3x. So considering that you've hopefully you've tried this already, but this is interesting because now we don't just have a function inside a function. It's kind of like we have a function inside a function inside a function, right? We did a problem before where, let's see if I can actually go back up to it. Where was it? Oh, sine cubed of x. There it is. So we had something like sine cubed of x, right? But now we're basically putting a coefficient here and we're saying, okay, do something with that. Well, here's what we have to do. So we're going to take care of this exponent first. Okay, so we have a function inside a function inside a function. Okay, so instead we can kind of rewrite our chain rule as the derivative of f of g of h of x. So it looks really, really insane, right? But all this really means is a function inside a function inside a function. Okay, and I'll even highlight that to make it more sense. A function inside a function inside a function. Okay, so that's that's that, and here this just becomes f prime of g of h of x, and you'd multiply by your derivative of g prime of h of x, and you'd multiply by the derivative of h of x. So we're now going to, I'm not going to erase that actually. We're now going to actually do that out here. Okay, so really what this all means is that we just have to take, we're going to say that this is kind of the same thing as x squared to start off with. Instead of tangent 3x squared, okay, instead of tangent 3x squared, we're going to view this as just, x squared, in which case the derivative would be 2x, right? But x, of course, here now is tangent of 3x. So it's 2 times tangent of 3x, okay, and that'll be to the 1st power. All right, and now we multiply by the derivative of tangent of 3x. Okay, what's the derivative of tangent of 3x? Well, that would be secant squared of 3x, but then we have the derivative of the inside to worry about. So it's going to be secant squared of 3x. Okay, and hopefully, if you're still following here, the derivative of tangent is secant squared, so that's where I'm getting that from. Okay, and then we need to multiply by the derivative of the inside of the tangent function, which is 3x. Derivative of 3x is going to be 3, so we just tack that on. So f prime of x, combining this all together, is going to be basically 6 times tangent of 3x secant squared of 3x. Okay, now you could simplify this down further by breaking it up into sines and cosines. I'm sure there's some way you could do it, but I'm not going to because actually probably wouldn't even be that nice here, but anyways. So for our last problem, just explain to me what an f prime of x tells you. Okay, I want this to be a conceptual question. I want you to understand, what we're actually finding here. Okay, we're able to take derivatives and all that, and that's going to take some repetition. That's going to take some practice, right? And you'll eventually get really good at it. But what is the derivative function actually telling you? Okay, and I want you to try to explain this in your own words. Okay, see if you understand what's going on here. Okay, you can write it down on a piece of paper. Okay, you can say it to yourself if you're alone, or if you're not alone, you can just be that guy and say it anyway. All right, or you can just think it. Okay, whatever. Just try to explain it in your own words. Okay, so here is what f prime of x tells you, assuming that you've already thought of it. Okay, what f prime of x does. Okay, f prime of x gives you the slope of f of x at any x value. Okay, notice that this x is the same as this x. Okay, so the slope at this, when this x equals 3, is the value, the y prime value, the output of that function, okay, when x equals 3 is going to be the slope of your original curve when x equals 3. Okay, let's draw those diagrams one more time before I get into the kind of the end of this video. We have one little half of y equals x squared. Okay, it's y equals x squared. And we have the derivative function, which we said was 2x. Okay, let's say we're talking about x equals 2. Okay, we go over two spaces on our derivative graph, and we find out that the y prime value, okay, that's what we call it. It's the x-axis and the y prime axis. Okay, y prime equals 4. Okay, because we have y prime equals 2 times 2, which is 4. All right, so that is the slope of this graph. Okay, it's the instantaneous slope. All right, at that x equals 2 mark. Okay, that slope is going to be changing. Okay, if you make an infinitesimally small increase in your x, okay, your slope will change by an infinitesimally small amount. Okay, but that's the whole kind of point of calculus, right? But we're studying rate of change here. Okay, and the derivative graph is going to give us the output of that, the y prime. All right, so instead of a y, we have a y prime. That output is giving you the slope of your original graph. It's really cool. There's a lot of applications for it. Okay, and so that's what we're actually finding here. So to wrap things up here, we talked about what a derivative actually was. We just ran over it again. We talked about power rule. We talked about product rule, quotient rule, chain rule. We talked about how to take a derivative of pretty much any function. We talked about the unique derivatives, right? We talked about the derivative of e to the x, natural log of x. We talked about the derivative of, just your trig functions in general, okay? And all of that combined, that's how you take a derivative, okay? And, now you know what a derivative actually is. So I really hope this video helped you. And if you were uncomfortable with anything that I went on in this video, you still have questions, leave them in the comments down below, and I'll try to get to them when I can. And if there's a lot of people already asking questions down there, if there's tons of comments and things like that, go back in the video, try to look at that again, try to look at that piece again that you're kind of unsure with, and see if it makes more sense to you now that you've already kind of been through the video, okay? And hopefully it will. All right, so thanks for watching. I really appreciate it. Make sure to subscribe for more content, okay? Because I'm going to be putting out more videos, and if you have a request, if you have something that you really need help with, put it down in the comments down below, and I'll try to get to it and make a video on it. Okay, you can check out the description for, I should have a Calculus 1 full course if you want to head over to that. Okay, and I'll have a full course listed of just everything Calculus 1, and also have a 100 question, maybe even more, final review video. Okay, so if you're studying for finals, that video is a great way to do it. Okay, and if I don't have those up yet, just leave a comment saying, hey, get that final up or get that course up. All right, and I'll try to get to it. And that'll definitely be some inspiration to go get it done. All right. I also have a Facebook group for the homework help. I don't know if you've heard about that yet. I mentioned it on my channel about a week ago. And basically what it is you ask your homework questions, okay? And I will respond in that Facebook group. I'll give you either a written response or a video response just like this. And that's kind of a great way to do your homework, I guess, or get help when you need it and not pay the expensive cost of a tutor. And lastly, if you don't want any of this amazing stuff, all right, if you just want to support me, I do have my Patreon, which I will link in the description down below. Okay, so thanks for watching. I do appreciate all the support. This video took honestly days to make, so I'm really glad to get it done, but I still got to go edit this thing now, and then I got to post it, and it's going to be a lot of work, but whatever. All right, anyways, thanks for watching, and I'll see you soon.